Let's discuss how to find limits algebraically, that is, using their equations. So in the last video, we saw how we can compute them by looking at their graphs, and that was relatively simple. It's just a matter of looking at it. As functions get more complex, their equations can be more complex as well, and it makes it a little bit more tricky. So we're going to look at a lot of different skills, a few different ideas for computing these limits. So let's start off nice and simple. Let's take f of x is equal to 3x plus 2. Now I'm going to do this one very informally. I'm not going to use really any concrete math. I'm just going to use some ideas. If we think about 3x plus 2, we know what shape this is. This is a line. And we know that lines have all their points included. That is, they don't have any holes, they don't have any of these jumps, or any places where the line stops or breaks. And what that's telling me is I could find the limit anywhere along that line. And if we kind of visualize that line in our minds, right, I'm going to do it very imprecisely. If we approach any point on that line from left and right, we know that it's going to be the exact same as the function value. So if I wanted to find the limit, let's say as x goes to 3 of this 3x plus 2, well, I can simply just plug in that 3, and we would find that the limit value is the same as the function value. We would get 11. But here we really relied on the picture a lot to help us with this. We thought about the picture first, and we realized that, hey, my limit value will be the same as the function value, therefore I can find it pretty easily just by plugging in. But what if the functions get more complex, or we just don't know what the pictures look like? So we need to start developing some rules for finding these limits. And so there's going to be a lot of different things that the book defines. And so definitely read over the book and make sure that we kind of write down all these laws. But just quickly, let's apply the limit laws, or most basic limit laws, to this linear equation. So remember our limit laws, we have the sum rule, we have the difference rule, the constant multiple rule, the product, the quotient, power, and the root rule. And so definitely look these up on your own and make sure that we know what they are. But what these tell us is we can break these limits down into very simple pieces. So I'm going to take the same limit and I want to calculate it again. So what the limit laws tell me is, for starters, I can always break up the addition of two different components or two different terms, because I can treat both of these as independent functions. 3x can be a standalone function and 2 can be a standalone function. So I can write this as the limit as x goes to 3 of 3x plus the limit as x goes to 3 of 2. Well, this is now incredibly easy, right? Even if this was part of a more complex expression, if we just have limit of a constant, we know that constant is just always itself. But this one's still a little bit tricky, right? We have some multiplication. Now I realize it's not really all that tricky, but let's just break it down to its most simple component. And so again, we can use our limit laws. We can say that this 3 is just a constant multiple, so that allows me to pull it to the front. So we'll have 3 limit as x goes to 3 of x plus the limit as x goes to 3 of 2. And so now we have these things written in terms of their most simple components. So we're taking a limit, this new operation, the limit of just x, and that's very simple. If we just have that x there, we just plug in. And we have the limit of just 2, so again, very simple. And then we have some math around that, but once we've calculated the limits, we've done the hard work. And so I'll have 3 times, just plugging in that 3 for the x, and then we have our 2. 3 times 3 is 9, plus 2 will give me the same 11. Now I do want to stress in this example, the first time, notice when I did it, I plugged in right away. I never write the limit again. But when I did it more formally, and what we're going to really need to pay attention to, until we actually plug in a number, until we actually go to evaluate the limit like I did in this underlined portion, I've got to remember to keep writing that limit. I can't just all of a sudden drop that, because then 3x is not the same as the limit of x going to 3 of 3x. Completely different. So we've got to make sure we keep those limits there every step along with what we're going to. That's very important. Let's take another example. Let's take the limit as x goes to 4 of 5x to the third minus 2x plus the square root of x. So now this is a more complex function. I have no idea what it looks like. I don't know what the graph of that thing would do. And so in my mind, I'm not 100% confident that I could just plug in. So I really want to break this thing down into its more simple components. And so I'm going to start by doing that by using my sum and difference rules. So breaking up the different terms as x goes to 4 of 5x cubed minus the limit, because I can pull that minus to the front, as x goes to 4 of 2x plus the limit as x goes to 4 of the square root of x. And notice I've written that limit every single position because I haven't actually found the limit. I haven't actually evaluated the limit. I'm just breaking it up. Now I can apply my constant multiple rule, and I can pull the 5 to the front for starters. Pulled the 5 to the front, so now we just have an x to the third there. Minus, I can pull the 2 to the front. So we have just the x. And I'm going to leave this one alone for right now because I'm just applying the power rule here. And then the final thing to do is to realize I still have an exponent, I still have a root. And so what the rules tell me is I can pull the limit to the inside of that exponent. So I'm going to look at the limit as x goes to 4 of x, and then whenever I get for that, I'm going to raise that to the third power. So it's just made it completely obvious to me that all I have to do is replace that x, and then whatever we get for that limit, then we're going to cube it. The x was already fine, that was as simple as we could go. But then here I'm going to pull the limit into the square root. My root law tells me I can do that. And so we'll take the limit as x goes to 4 of just x, and then we'll take the square root of that. And so when we do that, taking the limit as x goes to 4 of just x, we get just a 4, but we still have to cube that. Taking the limit as x goes to 4 of just x is just 4. And then same thing on the last, but we have the 4 now inside the square root. So notice in this line, I've finally dropped the limits because I have actually evaluated those limits. Now, if I see that you are dropping those limits earlier, if I did not write the limit here and I'm still using x's and I haven't replaced that 4, I will take off credit because that, without the limit here, would not be the same as when the limit was there. So we need to make sure we're writing this every single step. So we have 5 times 3 to the 4th is 64. 2 times 4 is 8, and then the square root of 4 is 2. 5 times 64 is 320, minus 8 plus 2. And so when we combine all of those, 312, 314, that would be my final answer. Now we do see that on this one is relatively simple. We just plugged in, after all that work of evaluating the different laws and bringing things around, moving the constants to the front, the constant multiples, and bringing the limits inside the powers. All we did is we really ended up plugging in the 4. And that's true in most cases. And again, we have some more laws and some more theorems that state this for us. So for instance, we have the limits of polynomials, which say if we just have a polynomial expression, we can just plug in. It's not quite polynomial because we have that square root, but it's very close too. We have the limits of rational functions, which say as long as we're not having our denominator go to 0, we can just plug into those. So in a lot of cases, it seems like we're just plugging in. And that's generally true as long as we don't have things like we have 0 in the denominator, or for instance here I couldn't have found the limit as x goes to -4 because that would have required me taking a negative inside a square root, and that would have obviously given me a problem. I would have gotten to this point right here and I would have had that -4 there, and I would say, oh wait a minute, this doesn't work. And so something's going on there. We have to think about it a little bit more. In this case, the limit wouldn't exist because square root doesn't have that square root of a negative value. So we have to be careful really where we see that we have those domain restrictions. That is the key, kind of like what we saw with the graphs. If we have just a graph that has a continuous curve or continuous line, those are pretty straightforward. We can find the limit anywhere along that point. But where we got to be paying attention to is where do those lines stop? Or where do those lines transition? Or where do those curves suddenly shoot off to infinity. Anything like that is going to give us the problem. That's going to be where we have to really pay attention. So let's look at one a little bit different that we have to think about a little bit more carefully. Let's look at f of x as a piecewise function. This piecewise function is 3x minus 2 for when x is less than or equal to 0. And it's square root of x plus 5 when x is greater than 0. And let's find the limit at the interesting point. So we know that this is a line that would have its limit everywhere along that line. This is a square root. It would have its limit everywhere when x is greater than 0 because that's its domain. The question is at the point of intersection. So I want to look at the limit at x is equal to 0. Now, really in order to do this, this is what I want to find of my function. But to do this, I really need to look at the one-sided limits. Remember when we were looking at the graphs, we had this potential for a limit not to exist if the limit coming from the left and the right did not exist. So let's find the limit as x approaches 0 from the left first. So if we're approaching from the left, that means we need to be looking at the smaller than side. In this case, the 3x minus 2. So we're going to be finding the limit as x approaches 0 from the left. And I can go ahead and put in the function. I'm going to use the 3x minus 2. So in this case, we've already really worked out that we're coming from the left because we've used that half of the equation. And because now this is just a polynomial, my rule says I can just plug right in. So we'll have 3 times 0 minus 2. Notice I dropped the limit because I've done the limit. And so 3 times 0 minus 2 gives me a negative 2. So we can find the one-side limit. That is pretty straightforward. Let's look from the other side. So x approaching 0 from the right. Well, that means I need to be using the stuff to the right of 0, this second part. So we're going to be looking at 0 from the right of the square root of x plus 5. So we're going to have the square root of 0 plus 5. And that gives me 5. So once again, we found the one-side limit. We found the right-sided limit. But these two things are obviously very different. And because they are not the same, what that tells us about the limit, or remember the two-side limit, the second we just say the limit and don't specify left or right, the limit does not actually exist at that point 0. Everywhere less than 0, we know that the limit would exist. We can find that by plugging in. Everywhere to the right, same story. But at that transitional mark, it does not exist. Now, does that mean that anytime we have a piecewise function, the limit won't exist at those transitions? That's not necessarily true either. So let's take 3x squared minus 2x plus 1. Let's look at if x is less than, we'll say, 2. And then we'll look at the equation 2 times x squared plus 1 if x is greater than or equal to 2. In fact, let me leave the equals 2 off because we don't actually care what the function value is there, right? We just care about where we're approaching. And so to make that really clear, here we see that if I were to ask the question, what is g of 2? We'd have to say does not exist. Same way we talked about with the graphs, it's very possible that a function value doesn't exist, but the limit does. Let's look for that limit as our x goes to 2. And again, we can agree that this is polynomial, this is a polynomial, so everywhere along these curves, the limit would exist. It's just at that transitional point that we're kind of uncertain. We want to know what's going on. So that's what I want to find. But in order to do that, I have to show that those one-side limits are the same. So if I were to ask a question like this on an assignment, now what is the limit as x heads to 2 of g of x? I expect those two limit statements. If you just say, oh, it's 5, I'm making up a number. But if it was, you just say 5, I'm not going to give you any credit. I have no idea where that's coming from. We haven't shown that those one-side limits are the same. We've got to show that those one-side limits are the same. So I'm going to start coming at 2 from the left. And so if we're coming at 2 from the left, that would mean we're using the less than equation. So we'd have the limit as x approaches 2 from the left of 3x squared minus 2x plus 1. And because it is just a polynomial, we can plug right in, so we'll have 3 times 2 squared minus 2 times 2 plus 1. So this would give me 12, minus 4 would be 8, plus 1, that would give me 9. So we can find the one-side limit. As long as the function exists in that area, we generally can. And now I'm going to look from the right. And our right would mean we're using the bottom equation, the 2x squared plus 1. So we'll have 2 times 2 squared plus 1. 2 squared is 4 times 2 is 8, plus 1 gives us 9. In this case, they are the same, so we can say with certainty that our limit is equal to 9. We've shown that. Now, the ones where we really have to do a little bit of thought is when our limits are going to infinity. And so if we have these sort of jumps, because we have a piecewise function or something else going on, we just have to find each of those one-side limits. When limits go to infinity, we've already said that those are actually limits that don't exist. However, by stating that it goes to infinity, it tells us something. And that's what the next video is going to look at. We want to look at going to x going to infinity, but also what does it mean as the function goes to infinity.